We've learned about electrochemistry by examining E cell. We've looked at concepts in thermodynamics like Gibbs free energy, and we know about equilibria and how to use equilibrium constants. Now it's time to understand how these concepts come together. First, we must understand that in galvanic cells, chemical energy is converted into electrical energy, which can then be used to do work. The amount of work that can be done depends on the product of the charge transferred and the potential difference. How do we know the charge transferred? Well, Faraday's constant tells us the electrical charge associated with 1 mole of electrons. We just take Avogadro's number and multiply by the charge of 1 electron, and this is what we get, expressed with 2 different sets of units. From here, we should understand that if work is charge transferred times potential difference, then this equation will tell us the amount of work a cell can do. We have N, the moles of electrons from the balanced redox reaction, and Faraday's constant, which gives us the charge transferred, and then E cell is the potential difference. This value should be negative, since the cell will do work on its surroundings. Now we also know that free energy is the energy available to do work. It should also follow that this equation is true. And lastly, if looking at reactants and products in their standard states, we get this. Now, apart from this, we also know that delta G equals negative RT ln K. So if we combine these two equations that both have delta G on one side, we can set the other sides equal to one another, meaning negative NF E cell equals negative RT ln K. Solving for E cell, we get RT over NF times ln K. With these equations derived, we notice that it is easy to move between K, delta G, and E cell, since there is an equation that relates each of the 3 pairs of variables. Let's try an example. Say we are looking at the following redox reaction. What is the standard free energy change and equilibrium constant for this reaction at room temperature? Well, first let's write out the half reactions and find the standard reduction potentials. The iron is being oxidized, so that's the anode, and the silver is being reduced, so that's the cathode. And these are the tabulated standard reduction potentials. Then it's just E cathode minus E anode, and we have our E cell. Now we can use this information to first find K by using this equation. So let's go back and plug in the E cell we just calculated, and then we can plug in this version of R, 298 K for room temperature, 2 moles for N, since 2 moles of electrons are transferred when iron is oxidized to become iron 2+, and Faraday's constant. That gives us 1.3 times 10 to the 42. Then lastly, we can calculate delta G by using this equation, again using 2 for N, and we get negative 240.6 kilojoules per mole. And now we know how to go between E cell, K, and delta G.